for those who know all about SciTech Cafe, you might be wondering where Kathy is. Don't worry, Kathy Adala, who normally runs all this, will be back next time. And so to start, I'd like to thank Kathy and Sarah Byrne for all the efforts they put into getting to this show. And a particular shout out to Carla Blata, who you all probably met on the way in. She really makes all this run. So today, I'm absolutely thrilled to introduce Dr. Rebecca Spencer, who's in the Department of Psychology and Brain Sciences at UMass. And she studies sleep, and she's going to tell you all about it. But before we do that, I need to thank our sponsors. We have quite a few sponsors: the Center for Integrated Quantum Materials, UMass, I can't remember the acronyms there. Center for Hierarchical Manufacturing, the Center for Integrated Quantum Materials at Harvard, Community-Based Learning at Montpellier, and the NSF-sponsored Materials Research Science and Engineering Center on Polymers at UMass. And my pleasure to introduce Dr. Rebecca Spencer.
All right, so it's great to be here. Long-term audience member, first-time speaker here at SciTech Cafe, and it's a great opportunity, and I hope this is just as much fun for you as it is for me to be up here. So tonight I am indeed going to talk about sleep, which is good for you since that's probably what you came for, but I'm also going to talk to you about the brain. There it is. And that is because I am a cognitive neuroscientist. So my department is psychology, but I'm a neuroscientist by training, which means that I study the brain. For those kids in the audience that are looking for a future career, I think it's a great one. So this issue of Wired magazine, some years ago now, pointed out some of the greatest unanswered questions in science. And one of them on this list, as you can see, is the brain. It's full of unanswered questions. But another one that this issue points out is the area of sleep. And sleep is one of the long unanswered questions of science. And the question is, why do we sleep? And they bring up the point that we all do it, but very little is known about why. And my goal tonight is to tell you a little bit about the answers that we do know to this question. So one answer to this question is that we sleep to grow. And it's true that if you took my infant daughter, which was a good number of years ago, in her sleep, she does have surge and growth hormones that would be a great opportunity to enhance her sleep. And if you have a kid that's sick and they get behind in their sleep, catching up on their sleep, you'll see a little growth spurt. But for most of you in the audience tonight, most of those little kids, this isn't going to convince you to go to sleep at night, right? You're not going to go to bed putting on those extra millimeters. So another idea, if you just Google the question of why we sleep, you might see, well, we sleep to get energy or to restore our energy or something like that. But most of us combat this one frequently. And you can just get a cup of coffee. So why do we need to go to sleep? And it's indeed the case that sleep is actually not very efficient metabolically, so we don't actually save a lot of energy by sleeping. The reduction in metabolism is only about 10%, which is very little given how inactive we are compared to our waking day. So that's not really a sufficient reason as to why we sleep. And so the answer that we've spent a lot of time on in my lab is that we sleep to learn. And there's this great quote by John Steinbeck that says, "It is a common experience that a problem difficult at night is resolved in the morning after the committee of sleep worked on it." And I find that very inspiring. So this is the long and the short of it. If you want to see some data, you're at the wrong talk. So I simplified it so that hopefully even the little kids can understand. We look at lots of different types of tasks. We can look at things like learning a new language, learning to play a sport, learning to play the piano, emotion processing. And in all of these tasks that we've looked at, if you look at them following sleep versus following wake, you see something like this. And as I said, there's not going to be much data, so this is the simplified version. If you sleep, you do better. If you don't, you do worse. And we've shown that for a lot of these different tasks that we've looked at. But what's interesting is, what is the brain doing for this to be able to happen? Well, we can take little kids into the lab and put some electrodes on them. There happens to be one of my favorite subjects over in the corner. And what you see is she's got little electrodes up here, one on her forehead, some by her eyes, and one near her chin. This is called polysomnography for the adults in the audience. For the kids in the audience, it's called mini sleep recordings. Because in order to understand what the brain is doing during sleep, you actually have to look at more than just the brain. So we put some electrodes by the brain that tells us what the brain is doing, but we also need to know what the eyes are doing. Because there's that stage of sleep called rapid eye movement sleep. And then we also need to know what the chin's doing, because surprisingly enough, in some stages of sleep, you lose your muscle tone. So we can even just look at muscles and say whether or not you're sleeping, and what kind of sleep you're getting. So we can do this with kids. There's our EEG, the eye movements, muscle movements. We have a portable amplifier. This is so we can record you in a different room or bedroom versus a nap, things like that. There it is. It's really fancy. And we can do this in young adults. And these are the different kinds of brain recordings you get. So you can see that the REM sleep looks very different than something down here called slow wave sleep. By looking at the different activity in the brain, you can learn more about exactly what the brain is doing while you sleep. So now with that introduction on the differences in what the brain is doing during sleep, what does that have to do with behavior? The point that I want you guys to take home with by the end of the night is that sleep is not singular. You can't just look at an animal and say it's sleeping or not sleeping. You should be able to say it's not just sleeping, it's in REM sleep, or it's not in REM sleep. Because as I teach you a little bit more about sleep science, these are things that you should be able to figure out. And all of those different stages to go through in the night are each serving a unique function. So if somebody wants to ask me at the end, well, how much sleep is enough? I hope you can answer that question yourself. The more sleep, the better. At least as long as you're still awake at some points during the day. Because it's all important. So, let me take you on a journey through the night. When you start the night, you're going to start up here. You're going to be awake. And then these are the different sleep stages you can dive into. Everything from that REM sleep down into slow wave sleep. When you start the night, as I said, you're awake, and then you dip down just a little bit. You might dip into stage 1. And what happens there, you often, especially if you're sleeping in a strange place, you might jerk yourself awake. When you do that, you might say that you had a dream you were falling out of the sky, or you were falling from your chair. And that's because your body was gradually beginning to lose muscle tone as you fell asleep. And if you're in a strange place, your body or your brain can consider that a bad thing. And losing muscle tone and in a strange place, wake up. And then you sometimes can cover up. Your cover up for that, why that happened, was to say, I was falling from the sky and it was a dream. But in fact, your body was trying to take care of itself and pull you out of this state of loss of muscle tone. So that's called a hypnagogic state that occurs early in the night, and it's not really our traditional dream state. So hopefully you're going to keep going through the night, and you're going to keep sleeping. And at this point, you're going to reach what some people call just simply your deep sleep or your slow wave sleep. And it used to be thought that we don't dream during slow wave sleep. But what we know now from studies like what we've done in our lab is you probably do dream. It's just that your dreams are so factual, you don't recognize it as a dream. So tonight, if you have to go into slow wave sleep, you might be dreaming of me up here talking to you about sleep science. And that's because your brain is just taking various events from your day and replaying them in just the way they happened. So if you dream during slow wave sleep, they're pretty boring dreams. It just looks like what happened while you were awake. Well, hopefully you keep on sleeping after this point, and you start getting into REM sleep. And that's where things get interesting, because this is when your really creative dreams start happening. So I've shown up in your dreams again, in case you can't tell. But now you might be confusing me a little bit with somebody you met at ABC some other night over at the bar. So I might be starting, instead of talking to you about sleep, I might be telling you about my crazy neighbor, and I might look a little confabulations out of REM dreams. But they usually have some link to reality, such as me showing up in a different context. So that part of where REM dreams come from is they integrate different forms or different past events to come up with novel combinations. So we'll come back to that. So again, hopefully you keep on sleeping. And you'll notice there's one stage I haven't talked about, and that's here in the middle. We call it stage 2. It doesn't have a very catchy name, so that's why you might not have heard of it before. But I think it's just as important. So one thing we think stage 2 sleep does is help us learn motor movements. So the stuff early in the night was very declarative, factual stuff. The stuff later in the night, the stage 2 sleep, seems to be where I might process learning to play the piano, learning my ice skating routine, things like that. And so the next slide, I'm going to show you an example of how we find that out. But I think this is a good time to pause and see if there's questions so far. Because you've been all so responsible and not asking questions, so I want to make sure that they answer. Yes?
What you're saying is that in slow wave sleep or deep sleep, you just like replay your day.
Yes.
But is there like no change, or is it always from your perspective?
That's a great question. The first part of your question is how far will you go depending on how long it's been since you've slept. So usually, and also keeping in mind that we go through 90-minute cycles. So what's not terribly obvious here is that this is happening in 90-minute cycles. So there's probably 90 minutes there, 90 minutes there, 90 minutes there, 90 minutes there, 90 minutes there. And in your first 90 minutes, you have to at least sleep 90 minutes before you're probably going to get to at least 60 to 90 minutes to get to some REM. And if you've not had REM in a while, because maybe you had a bad night's sleep, then you're more likely to hit it in your nap and hit it earlier. But if you've had a normal night's sleep and then you go down to take a nap, you'll probably not get it unless you take a very long nap. Yeah. And then the second part of your question was, why are they refreshing?
Yes.
So some of that is because what I'll be talking about a little bit is it's relieving a little bit of the pressure of we think what builds up in your brain that needs to be relieved. But they also lose their refreshing if you wake up in certain sleep stages. Then you have this sleep inertia or this grogginess that's hard to overcome. So it really depends how refreshing they are, depends on how long you nap for and which stage you went into. So I'll just answer 2 more questions now before I go. Is there another one? Yeah.
Will you address how you sleep?
How do we sleep? Not so much, but what do you mean by the how do we?
Besides the muscle relaxation, what exactly happens?
What exactly happens? So we do have a trigger in our brain that basically is not so much a turn sleep on, but turn wakefulness off. So we have that switch in our brain that turns wakefulness off. And it actually is related to melatonin, which is that drug you might hear about because you can buy it over the counter, that promotes sleep onset. And so they call it the vampire hormone because it comes out at night, and that's a sleep promoting hormone. And we can talk a little bit more about the melatonin aspect as I go. One more in the back. Either one, fight it out.
Well, you said that REM 2 is when the most processing happens, and that the first REM stage is when is the most creative. Which one of those? In which one of those stages are you producing more DMT and why?
So I'll just clarify the first part of that. So actually what I would say is these REM stages, for all we know, have a relatively similar function. And what I'm going to talk about now is something called the second stage of non-REM. So we only have one form of REM. We have three forms of non-REM. And so that's a perfect transition into what I'm going to talk about now. So you might wonder why I have this woman up here, other than that she has something to do with motor sequences. And there's a great tale that, this is Sarah Hughes, she's an Olympic skater, and there's a great tale, truthful or not, I don't know, but it's going to support my story here, that when she was preparing for the Olympics, she was peaking in her performance, she wasn't getting any better, and her parents were alumni of Cornell, where there's a great instructor, James Moss, who taught thousands of students at a time in a class called Psychology of Sleep. And he told the parents, well, if she's peaking in her performance, maybe she should sleep in a little bit. Because she was waking up really early for her morning practices, and so maybe she needed some more rest. And the story goes, like any good story, she skips her morning practices and goes on to win the gold medal. And the question is, why might that be? She's actually sleeping more. Is it just a matter of getting more total sleep, or something about the extra sleep that she was getting? So here's one way we can look at it, and this is to actually show you what we do in our lab. Unfortunately, we don't have an ice rink installed yet, and you asked for me to use in my lab, so we have to dumb our task down to this little key box, which might be a little bit more like learning to play the piano. Okay, and then the subjects have to learn a sequence of these little key presses. Just 4 keys though, not an entire piano. So they're learning a little sequence of movements here, and we're just interested in how fast they move, because if you're learning a sequence, you should get faster at it. Simple as that. And to jump through some data really quick, all you need to know from these bar graphs, whether you're a big kid or a little kid, you should be able to figure this one out. High means you were slow, low means you were fast. And if you look at the overall pattern, whenever there's sleep between the 2 sessions, the people got lots faster. Here's the difference between 2 sessions that people were awake, and they didn't get much faster. We can counterbalance the order, and we see that between these 2 sessions, when people are awake, there's very little change. But when people slept, again, they got a lot faster. So that's showing us that people get better. Our faster in this case is our measure of learning. People got better whenever they had sleep. So that's just one example. And the idea then is that by getting this stage in particular, we can go on and we can look at how much they got better as a function of how much of this late sleep they got. And it turns out the more of that late sleep you get, the better you get, which means perhaps a gold medal. So we haven't been hitting those out in our lab yet, but that might be the idea. So the idea is that in this late stage, the late sleep, the stage 2 sleep, you're getting better at our motor tasks. So hopefully you can see that across the night, all of these stages are serving a function. But some of you might still be wondering why. Why is that? Why would sleep make us better at these tasks? It seems a little strange. And I don't want it to seem just phenomenological. So we can look at animal studies for this answer. So if you take a little animal and have them run around the maze, you can record the cells in his hippocampus, the memory area of your brain, and just see what they're doing. And what you see is they're firing away and making this little neuron song. And so you see this cell fires, then this cell, then this cell, then this cell. These are just cells in the hippocampus, and they're firing in a certain order, while awake, while the animal's navigating its little maze. Well, little animal goes to sleep, and if you have those recordings still in the hippocampus, what you see is those same neurons are firing, and they're firing in the exact same order. So cool. The idea is like this. If I